Hello, everybody. My name is Park. I've been working on the applications for HPC for quite some time. I'm going to share with you, some of the findings that I work on one of the applications. So thanks for joining me into looking into this. So similarly to this topic, actually, later on in the day, there will be another presentation by Science and Computing AG, so about OpenFOAM. So our topics will be kind of like similar, which will be talking about performance on HPC applications. So I mean, which will be after the roundtable after my talk. So stay tuned. So first of all, I'm going to share with you some of the applications that we have worked on at the HPC Advisory Council. So we have over 130 HPC applications published. We work on analyzing and profile some of the characteristics on the application so that we can better understand if they are more sensitive into CPU or network or some other ways in the hardware. So please check it out at the HPC Advisory Council. There's a section called Best Practices. You can actually see a list of applications there. We tend to do them and compare against different generations of hardware when they, let's say like a Sandy Bridge or Ivy Bridge. We actually work on, comparing those, with different hardware being in the system. So feel free to check it out. So first of all, I'm going to talk to you about, some of the applications tuning that's involved and why we do that. So in order to achieve the best application performance and scalability performance on HPC application, it really involves understanding of the workload by performing some of the profile analysis, right? So we kind of understand how much is the times I should spend on CPU or network or I/O, so that by focusing on the largest area, it actually kind of help us into understand why tuning CPU actually makes the most benefit. So and one of the second point I put out is that we need to make sure that the nodes actually performing like similarly, because in HPC environment, when you have a node imbalance actually happens on one nodes actually would cause the rest of the the nodes to actually stall and then wait for the nodes to complete. So it's actually kind of significant to make sure it's not just the node imbalance on the application, but it's also the underlying systems, individual system in each in the nodes of the cluster performing kind of equally, so that you don't have one of the nodes actually running faster while the rest of the nodes actually running slower. So this stuff can happen. So you do want to run some sort of like a CPU memory network check or something like the Intel cluster ready cluster checker that to identify the bad nodes and correct that. And there are ways to to do that. So in the cluster checker. So and then we basically have published a list of applications that kind of demonstrate what I just talked about earlier. By doing like some profile analysis and to kind of understand why tuning one part of the hardware actually make it more effective on the application overall application performance. So for this talk, I'll be focusing on an application called PAM crash. Or I should say virtual performance solutions. So virtual performance solution, VPS, which formerly known, I guess, is originated from PAM crash. So it's a software package from ESI Group. It's used for crash simulations, so that the automotive industry are using it so that they can simulate a real car crash without having to use a live car to do that. So it's one of the CAE applications actually being used in the auto industry. So it has been well known for like the last 20 years. So they have been around for a while. So for more information, you can check out the links in here. So the objective for this talk is basically to understand what are the ways to improve performance using PAM crash, and then we also at the end, near the end, we're actually comparing what are the ways to make it more power efficient, meaning that there are ways that you can for instance, right? Adjust the CPU clock cycles to make it run faster. But at the end, it's how much faster you actually get in return. So we'll have some comparisons like that at the end. Let me say a few words about the test configuration. So the work is being done on the Dell PowerEdge R720 and R720XD. It's a 32-node cluster at the HPC Advisory Council Cluster Center. It's called Jupyter. So it's a dual socket hexa-core, 10-core. That means the Intel Ivory Bridge E5-2680 V2. Each node has 64 gigs of RAM and X1600 dual rank. It's running on RHEL 6.2. It's an Intel cluster ready certified cluster. It's using Mellanox Connect IB FDR InfiniBand. And for Ethernet part that we're going to use for compare, they will be running on the 10 and 40 gig, 10 gig E Connect X3 Ethernet adapter. The switch is the Mellanox Switch X Dixie36. For PAM crash, for VPS, the supported executable that they provide us are their platform MPI 8.3 and then OpenMPI 1.4 executable. And a version of the platform, IBM platform MPI that I used was 9.1. There's no problem using it because they're binary, compatible in a way that this supports like different, like a new version of MPI without problem. So the OpenMPI 1.8 that I use is OpenMPI that I use is version 1.8. That is based on something called Mellanox HPCX software stack. So that actually includes some of the acceleration software that it's kind of like Rich, the previous presenter have talked about earlier. So they that actually have support for collective offloading, and that shows some benefits later on. I'm going to show you that too. The application version is the VPS from ESI version 2013.01. The benchmark data set that they provide us was the crash neon fine. So that goes the introductory on the hardware and software configuration that were used. So a few words is about Intel cluster ready. So it helps deploy it and make it run so that you can make sure that the nodes on the cluster are performing kind of sort of equally, so that you get expected result and reproducible result from doing that. So the Dell PowerEdge R720 and R720XD is a 2U server that we use for each one of the nodes here. It's capable of having 6 PCI slots, so there are many ways of using it. So I saw one of the student cluster team actually using this particular one. Actually, a couple of them, couple of the teams, and they're using with the GPUs and this is a capable server with many different ways of use. I think either a traditional use or with CPU and also with many accelerators as well. So first slide I'm going to show you that I was able to compare was the performance on different network interconnect. So we're comparing 1 gig E and 10 gig E with the FDR InfiniBand. So FDR InfiniBand obviously is showing high performance, not just because of the higher throughputs that the FDR rate is able to provide. FDR is able to provide up to 56 gigabit per second. So compared to 1 and 10, so you get some factors of performance benefits from it. However, the benefits of InfiniBand also involves like having lower latency, which actually would be the kind of benefit some of the HPC applications. Right. So with the benefits of the low latency and high bandwidth, we actually can see that the improvement is around like over 7 times compared to 1 gig E, and the Ethernet stack doesn't generally scale beyond 8 and 16 nodes. So this is running with the option for no OpenMP. So in VPS, it has an option that actually allows you to run with just MPI, or with the options of OpenMP, which means that for every MPI threads, you are spawning additional, for every MPI process, you're spawning additional threads. That actually, later on we'll show that it actually turned out to be showing better performance when you actually end up scaling to multiple nodes. Later on, I'm going to show you that. So as I said, I guess, right here, with 2 threads actually spawn for every MPI process, it helps like getting more higher scalability, right? So in here, you don't see much benefits from, I see, 4 and 8 nodes and 16 nodes. They're somewhat equals when you're using the hybrid mode or not, or the MPI mode, right? So as soon as you scale out to 32 nodes, we start to see the benefits, right? So up to 8% higher performance than not using the hybrid mode. So you get a little bit benefits of doing that. For other applications that I have run before, you tend to see a little bit more as well. And come again, we are actually showing the network comparison. So this time around is with the 2 open MP threads for hybrid. So the benefits is kind of similar. We're actually showing up to over 5 times performance than 10 gig E and over 129% against 10 gig E. So the benefit for InfiniBand is always there. So to understand why there's a benefit of InfiniBand, we actually took a profile for the MPI. So what actually I'm showing you right here is that the amount of time the application spent, either user time or in MPI. So for 1 gig E, you will see that a majority of time of the total runtime, about 93% of the total runtime actually spent on MPI, meaning that it's the 1 gig E communications that's going on. For 10 gig E, you will end up with around 71%. So for FDR InfiniBand, we get around 33. So this actually shows you why you save the time for communication so that you can have more time for computation, which kind of show you why FDR is best performing. Here's another slide that shows where in those time inside MPI are spent. So you see a big splat of red here that corresponds to the MPI all reduce. So that accounts for like 31% of the time of MPI, or 24% of the total wall time, which is the actual time. So this is a major time-consuming area. So we are trying to look for ways to tune it, as I mentioned before, right? So similarly, you see this graph, which is the representation of how much percentage of the overall. So this agrees with what I have up there. So similarly, for 1 and 10 gig E, we have this red splat of all reduced, but the scale is way up there for 1 gig E, and a little bit better for 10 gig E. But the behavior seems to be the same. And you see still also seeing a bunch of unevenness for all reduced. It actually means that there are some imbalances for communication. So it could be either that some nodes are actually just waiting for the stuff to come in the network, or something like that. So later on, actually, right here we are showing the ways to kind of help reducing some of that time spent on all reduce. So something that the Mellanox presenter, actually Rich, talked about earlier. We can use something called like a collective offload. In here, this is called FCA, the Fabric Collective Accelerator. It basically offload part of the collectives, a few of the MPI collectives that are used. So all reduce is being one of them. So by enabling FCA with the flags right here, you kind of see that we're able to get some of the time back, right? So we saw around like let's see. About 24% of the overall runtime are spent on, because of the communication. So we save like 9% from here by using FCA, which is not bad, but still, I think there are ways to make it better. But I think because all we do is also group communication, they're actually very expensive to optimize. So there are ways that there are things I do here to make it work because there seems like there are no imbalances going on. So some additional FCA flag I was told to try, and that's what I have found. So another graph just to show you what are the messages that are concentrated. So for the all reduce, the one in red. So from right around here to there, I guess, this is when they have all of a sudden a very high percentage jump. So a majority of the messages actually happen around there, at 164 bytes. This is how I read this graph. So, and the rest I think you do not need to see because they don't spend a lot of time doing that. So. Okay, so for this graph, we're actually comparing the default MPI that's provided by VPS, which is platform MPI, and compared to the open MPI with tuning that we just talked about, and see how much of the gain or indifferences are there. We're able to see some benefits of using FCA due to the FCA collective accelerator offloads. They were done about 10% comparing to IBM platform MPI. So it does show some values of using collective offloads. So just to point out that a note saying here. So the default VPS open MPI that was used is 1.4. There are some works that were done to make it work so that it runs on the OpenMPI 1.8 version that are used with the collective offload. So this is the part I talked to you earlier about. So there's benefits of using turbo mode, obviously, but we're trying to see at what cost, right? So on the right-hand side, I'm comparing on a foreigner case whether or not I have the turbo mode, which is part of the the features from the Intel CPU has, right? So by enable it, we get additional 8% gain throughout pretty much like from 8 nodes, 16 nodes, and 32 nodes, and pretty much the same percentage gain as we scale. So that's not much, the gain is constant. So at the cost of probably 11% higher power draw, power usage by doing so. So this is the measurement I was able to find from the iDrive management interface from the R720 system. So here you go. Similarly, for the CPU clock, obviously there are gains to be had when when I deliberately set it to the CPU clock rate to like 1200 to 2000, 2700, 2800, and then finally 2800 with the turbo on. So obviously the one with the higher frequency and the highest turbo mode would actually give you the most benefit. But at what cost is more like you save around like 10%, pretty much 10% for the two different CPU clock. And then if you lower it by to the 2000 megahertz, then you suffer. Well, actually, you gain a lot more. Just some of the findings that I was able to do. So this is another interesting things I've seen. So there are ways to run a crash simulation. So using a single precision and double precision. On some of the models that I was able to work on, you can only run on a double precision because if a single precision model was used to calculate, you would not probably have a solution that would be able to converge. So the solution will not be able to solve, and then you won't end up with a simulation. So, but for this one, I was able to use both single position and also double position. So by using more nodes, you see that the time that you spend on double is actually slower, or the time that you spend on single is actually faster, either way. So the gap between the two kind of increases as you scale. So the way I would take it is that when you have more machines actually involved in part of the in a part of the job, more data with double position requires more data to be sent across the network. So maybe the amount of data caused that to grow. That actually explains why there's a wider gap as you scale to more nodes. So I/O for the computer-aided engineering tools is actually kind of important, because a lot of data has actually been stored on the file system, and it's a big component for it. However, I think the data sets I was given wasn't doing too much of the writing back to the file system for storing as intermediate data or restart data. So their periodic data actually been written throughout, either on the rank 0 node or the rest of the nodes, but there's nothing really compared to what a real simulation that I would have got. But this is good in a way that it actually shows that both the rank 0 node and also the compute node, the rest of the compute node actually does some I/O. So a parallel file system should be able to benefit for this. Just some quick slides about additional MPI profiling. So this is what we have shown earlier. So with different node sizes, we kind of see the same messages actually being used for different ranges. So this is no surprises again. This is just another representation of the previous one. It's just that we are, decomposing on the one node case and two node case about how much data being passed around for each rank. So obviously there seems to be some, processes and balances. Some nodes actually spending more time or transfer more data to the other ranks. Another representation of the previous slide. So this basically sums up how much data collected throughout all these ranks for, let's say, one node case and two node case and 4 and 16 and so on. So as you grow to more and more systems, you'll get more and more data transfer on the network. Okay, so this is a point-to-point data flow that shows how much data being concentrated and sent across the network. So let's say between the rank 0, you talk to the other ranks that kind of close to each other. So if that's a way to bind the process in a fashion that is actually very close to closely to the ones that actually they talk to, then we'll actually hopefully will make better performance. That's the way I look at it. But just a summary slide of some of the things I just talked about. So FDR InfiniBand, we were able to show better performance for VPS to scale. So an OpenMPI with the tuning that we're able to see about 10% of performance gain using FCA, and in the hybrid mode, as you scale to 32 nodes, you actually will see some benefit of doing it. So this pretty much wraps up what I want to talk about.
Okay, any questions for Pak?
How do you select the most suitable parameters for commercially available MPIs? For instance, for platform case, Because you have provided example of the way you have optimized OpenMPI. There are several cases, but the platform of MPI was run out of the box, as far as I understand.
It was run out of the box. They have some tunings already in the script that PEM-Crash would normally provide to their users.
So it's part of the IC.
Part of the ISC script. So I have mentioned earlier there are additional things such as the FCA that I added into the script. So it's a script called PAM World. That's what I add my changes into it. So platform, they do have some tuning parameters already set in this PAM World script. So I was running it with whatever that typically a user would do.
For the configuration you have had.
For the platform MPI runs right here. That I'm showing you right here.
I just want to have it try to play with their parameters as well, because sometimes maybe it's not suitable for particular configuration, so maybe some extra tuning is required.
That's a possibility, yes. Especially, let's say for FCA, I kind of know that there's supposed to be a version of FCA that will work on platform. It's just that when I tried, and there was some, the FCA version I have is kind of new. It doesn't play too well with platform. So, but with platform, I would say if they have FCA 2, they have support for FCA obviously, but if they have FCA 2 that actually works with the latest version, then we probably would expect again 10%.
Yeah, because the only my point is that it would be great if you contacted MPI developers directly in order to figure out which parameters are optimal.
Yeah, luckily for OpenMP I do, but for platform, yeah, no problem.
Would you agree that when you start an effort like this to profile an application and try to optimize it, that one of the big first steps is finding good input files and figuring out how to install software, how to use the software?
Yes, I agree.
And so are you sharing your part in that effort? So the input files you collected, the script you wrote to run the analysis?
Yeah, for the input file, it's a little tougher to get if it's not for open source project. I mean, it's not from open source project. This I actually do have to reach out to ESI group, and that's the one they were able to provide me. I did try to, especially for the I/O part. I think I was trying to see if there's another one that would more similar, provides more similar performance or output that like a regular customer would have that does a lot of I/O. Because at the time I actually do want to profile I/O part of it, but this doesn't seem like it's a lot of I/O that's been generated. Yeah, I agree. Yeah.
For the reports that are on the HPC Advanced Council website, are those inputs available as well?
For the open source ones, they are. We try to write out the instructions for the open source one. For the commercial and ISVs ones, they're a little harder because they're not really publicly available. Nothing I can do about it. Sorry.
One more on, maybe you already said this, and I missed this. When you did the Ethernet, 10 gigabit Ethernet, 10 gigabit Ethernet,
yes.
Did you use any of the low latency Ethernet techniques?
Do I use the local?
Low latency.
Low latency.
Like iWarp, is that something that?
No, I do not. No.
Okay.
No, I do not.
And that might be a way to improve performance.
Yeah.
We'll talk offline.
Yeah. Okay. There are times I do, but the times for this is a little short, I think, when I do that. So anyway, yes. Okay.
Great. Thank you, Pak.
Thanks.